Well, today we have a seminar which is somehow related to quantum technologies, quantum methods for neuroscience. And today we have three speakers. The first speaker will be Joan Falcó-Roget, who is practically at the end of his research leading to PhD degree at Sano. Before that, Joan has obtained a bachelor degree in fundamental physics from University of Barcelona. Then he got Master of Science in Physics and in Biological Systems from Autonomous University of Madrid, and joined, after that he joined Sano. And as I have told, he's almost at last steps leading towards his PhD. And we have two Master of Science students, at the Faculty of Computer Science of IGH University of Kraków, namely Barbara Wojtarowicz and Kacper Jurek. They are both still Master of Science studies at IGH University, and they are still interested in quantum technologies, quantum methods. So, well, it's about introduction. As usual, if you have any question during the talk, please put it on questions and answers or on chat. I will try to present these questions, and of course, after the talk, there will be a time for discussion. Joan, Barbara, and Kacper, screen is yours.
Thank you. Hopefully you can see me well.
Yes.
And the presentation also. So thank you, Marian, for the introduction. So we organized the talk in two separate presentations. Initially, I will be talking 15 minutes about the conceptual and theoretical background, and then I will give the screen to both Kacper and Barbara, and they will tell the details, the implementation details of what we have been working on for the last year and a half, more or less. So this is a joint project that started, as I said, a year and a half ago, and we are doing jointly with Kacper, Barbara, and Katarzyna Rycek and Karol Zapała from Cyphronet and AGH. The library we developed is called Qommunity because we are interested in using quantum resources to detect communities in networks and especially in brain networks. So as I said, initially, I will just talk how we can, from this object here, that it's a graph and a network, how can we use quantum resources, and in particular, D-wave annealing devices to understand structure and perhaps function in brain networks. Initially, first of all, I need to explain what the modularity function and how we define communities in a network. And in terms of visualization, graphically speaking, it's quite easy. So we start from a network that is just a set of nodes and their connections, and we end up with a divided set of communities that allow us to understand how the structure is in this network. So, okay, visually speaking can be somewhat easy to do this, but we need to quantify it in a quantitative way, right? So for that, we use the modularity function, which was defined 20 years ago by Neumann and Girban. And essentially, it is this function here that for every community in our whole set of them, we basically measure how many edges are inside each community with respect to the connectivity of the community and the rest of the network. So it's in essence how many edges are inside this community with respect to the expected for the whole network. So we have a way to quantify modularity and how modular this network is. So in a very unambiguous way, right? So modularity can be a number, but it cannot be two numbers. So we define the problem of community detection through modularity maximization. So we understand that the community structure of the network is that community that is associated with the highest modularity. So essentially, we have to maximize Q. The problem is that to maximize Q, we do not know how many communities there are. Otherwise, the problem would be solved. So that means that it's an NP-hard problem. It was actually proven that maximizing the modularity is NP-hard. Therefore, the use of quantum annealing is very justified because it supposedly solves NP-hard type of problems. To understand how we can do that, let's simplify the scenario and just assume that there are only two communities to discover. For that, then the problem becomes very easy, algorithmically speaking, because we assign for each community one variable which we can understand as a spin, as either +1 or -1. So let's suppose that red are +1 and blue are -1. We randomly initialize it, we compute the modularity, and we change the network in whatever way we want. We measure the modularity again, and we keep repeating this process until we hopefully arrive to something that makes sense and has the highest modularity. Now, of course, as you can imagine, probably this process is far from optimal. It's very computationally expensive, and it only applies to communities, right? As I have said. Great. So how can we move forward? It was shown actually quite early, before even it was proven that it was NP-hard, that the modularity function maps to a fully connected system of spin glasses. And for now, you would have to believe me, but you can find a demonstration in both of these works from our group, that it actually maps very well, and it actually does it in where the interaction is quadratic, so we have no linear term. In the case of two communities, it's a very well-known system in physics. In the general case, we have also a very well-known system, but now we have a discrete case. No? So this is probably resembling a Potts model rather than an Ising, although it's a generalization of that. I didn't talk about the gamma, the resolution parameter, but it basically measures how important is the size of a community. So for large gammas, we give priority to smaller communities. So it's a way of considering different topological scales of the network. And because we're interested in keeping that, we will always express gamma in our expressions, because we want an algorithm, we want a procedure that can be adapted to what is called multi-resolution methods. So for us, it's very important that all the analytical derivations, as well as the computational implementations of those, have the explicit, they have explicitly this gamma parameter. When we have the modularity function expressed as this Ising system and so on and so on, the structure of the network is encoded in what is known as the modularity matrix, which measures, once again, the connectivity with respect to this randomly expected connectivity in the network. So we have simplified the initial formula where the number of communities had to be known to this generic formula that is independent of the number of communities. So this is a step forward, and we can use it. Now, can we use quantum annealing directly in these systems? Well, from a practical point of view, we can, thanks to the D-Wave interface. And we actually showed in 2023 that you can optimize directly this discrete case using hybrid methods. However, they are quite slow. They work quite well, but they are essentially a black box. You have no control over what the D-Wave is doing, rather how much time is using in terms of actual quantum computing time and classical division of the problem, so that we can solve it. So we want to go one step further with this as well. Just as a brief note, like not only the modularity maximization problem maps to a spin system, actually many NP-hard problems can be tackled within the same formalism. It has also been shown, and this is quite easy, that any spin glass system maps to what is known as a quadratic unconstrained binary optimization problem, which you can feed directly into the quantum processors. Now, this fitting of the problem expressed in binary variables to the actual quantum processor is actually not a trivial problem itself. And Barbara will talk more about this, what is called the embedding of the problem to the quantum processor. But if we assume that this is possible, then we just need to remap the previous expression that was using spin variables to this QVO, and we get this, in this case, we have a linear term because of the gamma. No? So if gamma equals 1, which was the original expression, we just have, again, a quadratic term, which maps very well directly to a QVO problem and to the quantum processor. However, what happens in the general case where we would expect to detect more than 2 communities? Well, this creates a big problem, to be honest, and affects the practicality of quantum annealing in a very critical way. Because now we need to encode the belonging of every node to a discrete set of communities. So we can no longer use 0 and 1, and we cannot use integer numbers because we need to be still in this binary programming framework. So the solution, or one solution, is to encode the problem using one-hot encoding. So every node here is encoded with a vector full of zeros except 1 in the position that codes the community it belongs. So in a graphical representation, this was shown here, is that this would be one node of the network, this would be another node of the original network, and each subnode here would represent whether a binary variable, whether this node belongs to community number 4, number 3, number 2, number 1, etc., etc. And the original topology of the network would be these black lines. But a network can only belong to one community, so you have to impose these constraints that ensure one node belongs only to one community and not more. And in the QVO formulation, this is introduced with Lagrangian multipliers that ensure that your constraints are met. However, we do not know the values of these Lagrange multipliers. So this means that we have to guess their value, or we just have to keep trying until we get it right. If we assume that this works, then we can map the general case also to the D-wave. But actually, this is a huge problem in practical terms because the constraints are not always met. Second, we do not know the values of lambda. And third, because we are using one-hot encodings, we are actually using many more variables than we actually need. For example, in the case that we would want to detect 5 communities, we would need 5 times more binary variables to encode. And lastly is that since we do not know how many communities, we want to find why should we restrict ourselves to using a 10-dimension vector or a 11. So we have to guess also the number of communities. And if we guess too high, we are again wasting a lot of practical resources. And if we guess too low, we might be missing a lot of the structure of the network. So these are 2 critical problems that we address here. And how do we address this? Well, the idea is that because we can solve very well with quantum annealing the problem of 2 communities, we are going to recursively subdivide every time the network. But we have to be very careful with this. So let's suppose that we have a network and we have divided it in 2 communities, and the community, the split is optimal, the annealing process has worked well, and now we have to continue. So naively, one would think, okay, so let's just take this subgraph, so this set of nodes, we compute their adjacency matrix, everything, and we do the QVO problem again, and we optimize. Well, this is wrong. And it is wrong because doing this does not consider the connectivity between the 2 modules we discovered. So essentially, these edges here. So the correct way to proceed is to measure explicitly the increase or decrease of the modularity after splitting this community into 2. Mathematically speaking, this can be expressed with this simple subtraction, which is the modularity of splitting this community, not subgraph, into two with respect to the modularity of the initial division. In this case, would be two communities. Again, I don't have time to go into the mathematical details of this process, but you can check our preprint. But we show that this actually is expressed as a pure quadratic cubo. So there are no linear terms. The resolution parameter is rooted inside the modularity matrix, so there's no gamma term. And these are binary variables. So it is actually a very nice way of solving the problem that I mentioned. The only difference with respect to the original cubo problem is that the modularity matrix now is called generalized modularity matrix, using the name from Neumann that Neumann gave to this object. And essentially, as you can see here, it encodes the connectivity of the module we are interested in dividing and sort of considers the connectivity between the module and the rest of the network. So again, we are solving the problem of dividing the subgraph in an isolated way. And if we didn't do this, the subdivision would be actually wrong in terms of the whole network. So if we express this recursive process, so we start with a network fully connected, no communities, and we start dividing, there is actually an assumption that we need to consider and we need to be aware of, is that we have to express the final modularity as an incremental process, where for every k that we split, right, we add the increments in the modularity function. And why we can do this is because the modularity is actually an additive quantity. It's a linear quantity. So basically what this says, and because it's a linear quantity, because QP itself is a linear quantity, then minimizing Q essentially is the same as minimizing every step of the process. Where is the assumption here? The assumption is that we can minimize the modularity through incremental steps rather than all at once. So we have to be very careful with this. And because we are dividing the network in a recursive and in splits of 2 every time, the assumption here is that the optimal community structure can be found this way. Now we show that this actually works very well, but it works extremely well in networks that have some inherent hierarchies that we can exploit with this method. So I know I have gone a bit too quickly, but hopefully you understand how we solve the problem of multiple communities. And essentially what we do is just we recursively split into 2. And when we do that, we have to be careful that we are optimizing the correct function at every step. In terms of pseudocode, this is quite simple, and I have put here a small abstract of it. And we basically initialize our network and we define the routine that takes as input the graph and the number of nodes. We compute the modularity matrix both for directed or undirected networks of this graph, and then the generalized modularity matrix, so all of these are functions. We can compute the cubo element, which I've shown that maps very well, and then the quantum optimization happens here, and it's binary, so we know it works very well. And the output is the division in 2 of the networks. So these are community 1 and community 2. Now, if both communities are non-empty, that means that the graph can be split into 2. We call the routine again, but we call it inside the communities, not inside the whole graph. And because our cubo problem correctly considers the whole topology, the whole structure of the network, we can recursively apply these until one of the 2 communities is empty. And then the algorithm stops. I have not shown this, but this process, this P of K that I showed before, actually naturally stops when there is no division possible. And it maps to the full cubo problem of the whole network initially. So we actually have a natural starting point, a natural division point, and a natural ending point for this algorithm. And all the demonstrations that I have not shown here, we do show and we prove them that this is the case. very briefly, before we go into the implementation details, these are some subset of results. And what we basically do is that every row here is a type of network, so different topologies. So this is a power law network. This is, as far as I remember, preferential attachment. So it is able to create, again, hierarchies in certain scenarios, completely random networks, and directed networks. So that means networks that don't have symmetric connectivity matrices. So this is also a plus in our framework, because we can consider in the same way both directed and undirected networks. Essentially, what I'm showing here is that for this network, the hierarchical annealing that we call, that uses pure quantum resources, performs exactly the same way as optimal state-of-the-art methods, and even slightly superior in this case. So in blue, I'm plotting whether the annealing solution is better or worse than the other methods for different sizes of the network. So we actually see that most of them are blue, meaning that the annealing is better, and some of them are red, meaning the annealing is a bit worse. And we have some equivalent performances in black. And here you just see the graph. No? So we can see that in the black line, sometimes is above, sometimes is lower, but in any case, it's very comparable performance. And there is this isolated case that for whatever reason, the annealing is better. And you can see it here in the structure that the annealing returns a much more modular configuration. Where is also the advantage of our proposal is that because we don't use one-hot encodings, we can encode bigger and bigger networks. And we are actually only constrained by the properties of the quantum processor itself, rather than any inherent limitation of our method. So we just applied it to brain structural connectivity. And here I'm showing that more or less we are recovering the two hemispheres, the frontal and parietal lobes. So our communities make some sense. And also the cerebellum is identified separately. And because it's recursive and hierarchical, all the algorithm itself is interpretable. So using quantum resources, we actually can analyze the hierarchies of the networks we want to describe. So we think that this is a step forward into an application that can be useful for network neuroscience, and because we want to use network neuroscience for medical purposes. So hopefully, or maybe in the near future or in the future, we can slowly incorporate quantum technologies into these daily uses cases. So to summarize very briefly, we thoroughly derived the spin and QUBA formulations for the modularity function, and also considered an arbitrary resolution parameter for the general case. We propose and validate a quantum classic algorithm because we use recursion using quantum technologies. That's why we think it's quantum classic to solve the problem. And we do not use one-hot encoding nor Lagrange multipliers. And lastly, that this is the step that will happen now, we develop, test, and publish an open source Python package that aims to join multiple community detection methods, both classical and quantum. Good. So I will stop here. I don't know if there are any questions that I can take.
From Stefan Zachow, we have a question. What are the current limits of the recursive approach with requests to the size of a graph? Did you evaluate memory requirements?
Yes. So this is a great question, and it's one of the comments that we got from the review that we are working on. So they were positive, but one of the comments was for us to explicitly evaluate how big we can go. We found out that we cannot go bigger than 169 nodes. So we cannot embed a network that is bigger than 169, but only because the advantage uses an embedding that we can partially control. So it's using, we think, a lot of physical qubits for one logical qubit. Mm-hmm. But we are working on whether we can go slower on this. We don't think we can. So the maximum would be 169. And the second part of the question, in terms of memory consumption and time, The annealing process is very short, so every request is very short. But because we are making multiple requests, we think that the time comes from that part, because we have to, we don't know if it's a queue or not, but we have to make a request and wait that the request is actually accepted by D-Wave and then embed the problem. But we only have to embed the problem once. This is also something that we discovered, because the modularity function is a fully connected graph. There is we can embed the full click to it, and Barbara will give more details about this. And then we just like use smaller click embeddings from that one. So we actually speed up a lot the embedding process, but I think we are constrained by how many requests we are doing. So if we had either a local machine or some other solution, the computational time would be actually reduced a lot. But there is no practical problem in calling multiple times D-Wave, if that answers the question.
Well, Stefan, many thanks for question and many thanks for reaction. And I understand that now we switch to Barbara or to Kacper.
We are switching now to both of us. So thank you, Jean, for the introduction. And please let me know if you can hear me and if you can see the screen as well.
Well, we can hear you. We can see your slides. So go on, please.
Yes. So thank you, Jean, for the introduction. Now we would like to present how we actually proceeded with the software and its implementation.
Okay, so hello once again. My name is Kasper, and I want to talk more about our project. So our motivation for creating our library was to detect the partitions of our brain. So we wanted to find the functional areas of our brain. So it will help us with finding partitions of our brain, or to diagnose neurological diseases. So because we can represent the brain as a graph, we are able to find communities inside that graph. So we are able to find the parts of our brain. So one community is one part of our brain, so we are able to find the areas of it. So the key objectives of our problem was to develop a tool to perform experiments on graphs, because there are a lot of libraries that provides the community detection algorithms, but every library provides a different interface. So if we wanted to perform experiments, we had to program program every experiment by itself. So there was no tool that provides a same interface to make the experiments quicker. So that was the main idea behind our project. We wanted to develop the hierarchical partitioning because quantum solvers works on binary variables, and we didn't want to use the redundant encoding because of the number of qubits that we were using. So if we will use a redundant encoding, the size of the problem will decrease, because, well, we'll use more qubits on encoding instead of putting the problem itself. So we wanted to find the way that we will use the least number of qubits for the problem. So we come up with the hierarchical partitioning for that one. And we wanted to convert the problem into QUBO problem, because we were using the D-Wave solutions, and it required the QUBO constraint, quadratic unconstrained binary optimization form, we wanted somehow to represent the problem with Cubo, and we done that. And what steps did we take to solve that problem? We developed the library itself. It's called Qommunity and provides to user the quantum and classical methods to find communities inside the graph. We expanded the QHyper, the library, to conduct optimization experiments using quantum and classical solvers. We use that because, the quantum computing lab in CyberNet already work on that, and we wanted to expand that that library with our problem. We implemented some problems and solvers inside that. So yeah. And we wanted to integrate the wave solvers with our problem because this is a company that provides the quantum solution, quantum methods, quantum solvers for consumer use. So we don't have to have a quantum computer to use the quantum resources for that one. And as I mentioned before, we created a community. This is a library that solves the problem with the interface. So we provide this simple interface for every method that we provide. So it's easier to perform experiments in that case. And we provide the quantum, hybrid, and classical solutions. So as we can see here, there are a lot of methods that we use. There are well-known methods, for example, Wayne, Bain, and Leiden, and there are some not well-known because we implemented that by, for example, Advantage and TQM. So now we are able to use a fully quantum computing for community detection. That was never provided before.
So as we have said, in Community Library, we focus on solving the community detection problem as a combinatorial optimization problem on the quantum processor units. And the thing about using the pure quantum solver is that it operates on binary variables. So what we have done is we bypass the variable encoding by implementing the hierarchical community search, which is indeed a community structure detection method, which means that we rather let the graph divide naturally into subgroups than steer with the hyperparameter of how many communities to detect, okay, that Joan has talked about. So the limitations stemming from the fact that we need to use some sort of encoding. Well, the community detection problem lies naturally in the discrete domain, as networks typically have more than 2 communities. So in order to transition to the binary domain, some encoding must be applied. And one approach is with the so-called one-hot encoding, where we tend to represent each variable in the initial graph with k helper variables, which are binary, under the condition that they sum up to 1. So exactly one of them is equal to 1, to ensure the fact that actually each node belongs to exactly one community. So if we add this term to the objective function that we initially optimize, we can actually see that it needs to be added with some sort of weights, and these weights are called the Lagrangian multipliers. However, establishing them, as Joan explained, is a problem itself, because we need to guess them, or we need to develop a procedure to find them, to establish them. So this is a problem itself. And to bypass this, we introduce the hierarchical divisions. So we stick to the binary variables here because we proceed with binary divisions. Second of all, we're not making any assumptions about the number of communities to detect. So we are not steering with any hyperparameter of how many communities to detect, how many variables, slack variables to present in the encoding. And we are letting the network divide into subgroups more naturally. We are not steering with it. The community library also focuses on visualizations. Here we can see some very basic visualization that gives us insight of how to interpret the communities. We can see them on the picture. And we can also interpret the dendrograms. So in general, the dendrograms are a popular way of representing the clusterization process, both in the agglomerative and divisive approaches. In our library, we focus on the recursive, hierarchical, so divisive approach. And we can see on the y-axis, on the x-axis, the so-called leaves grouped into communities. So these are the nodes that and their final community division. And we can also see the clades, which are the so-called, let's say, groups that occurred on each division level. And on the y-axis, we can see the increments in the modularity metric that happened on each division level. We can also see that it's additive, as we have already said. So it's a nice way to visualize how each hierarchical division contributed to the overall modularity score that we obtained.
Okay, so I wanted to say more about the QHyper library. As I mentioned before, this is a library developed by quantum computing team in CypherNet, and this is a library to perform optimization problems using quantum and classical methods. You can find there three main components: problems, solvers, and optimizers. And for our problem, we developed a community detection problem because before there wasn't a solution inside of that library. Because of the simple interface in QHyper, we were able to do that in a simple way. So already it is implemented and implemented inside that library. Another thing that we introduce into that library are free solvers. So the two of them are provided by the Wave company. So the advantage, the pure quantum solver that only use the quantum computing methods, and DQM, the hybrid solver that uses the quantum and classical methods inside that. And we also implemented the Gorabi solver, the well-known Gorabi for that library. So we implemented the usage of that Gorabi. So if you will use the QHyper for any optimization problem that you want to solve, you are able to use all of these solvers on any problems, not only the community detection problem, but any other problem. For example, if you want to use that for a backpacking problem, you are able to do that with those solvers and any other solver that is already implemented inside that library.
Here we can see the system map architecture. We can see that the QHyper library serves as a computational model provider for some of the methods that we implement. And the other methods, we actually implement access to them. So this is how it represents alongside the dendrogram module. And the anatomy of our library is that we have the samplers through which we choose the method we want to use. So the classical, hybrid, or pure quantum resources. The searchers that implement the engine of the hierarchical recursion, and in terms of the hierarchical partitionings, and iterative searchers, which facilitate experiments on maximizing modularity of networks by addressing the stochastic and probabilistic natures of the solvers and generally methods, as we produce a pool of solutions from which we pick the best solution as our maximum network modularity. We have performed code profiling to actually address some of the vulnerabilities. And the picture depicts the execution times of the hierarchical annealing with Advantage Solver. And we can see that majority of this time is consumed by determining the so-called standard minor embedding. The rest of the time, including calculations of modularity matrices, Kubo formulas, and cloud communication with the solver, are on the left. The process of minor embedding is embedding one graph, called the source graph, into the target graph. The target graph in our case is the Pegasus topology of the quantum processor unit architecture. The source graph, on the other hand, is a graph representation of our Kubo problem formulation, because as Kubo is quadratic, we can represent it as a two-dimensional matrix, and storing a matrix, we can easily map it to a graph. Then we embed one graph onto the target graph. The embedding process can be presented in such a way that, here is an example. With yellow, we have a problem representation with quadratic interactions marked as edges, and with linear biases related to the variables. That would be the diagonal of our Kubo matrix. We also have a representation of physical qubits. Here we've got a very well simplified picture, just an example. And what we do is we embed, or actually D-Wave embeds, the variables, problem variables, onto the physical topology of qubits. And that would be called logical qubits. So the variables are mapped to logical qubits. And as can be seen, well, actually, many of such mappings exist. However, sometimes one variable needs to be represented by more than one qubit, and they are called chains. D-Wave Ocean package proposes us 3 ways to actually handle the embedding: the standard heuristical one that we have already mentioned, the so-called click embedding we will talk about, and there is also an option to apply your own custom embedding. However, it is a math problem, including graph theory. It is not an easy task. Here are some visualizations to gain some intuition of how these embeddings look like on the quantum processor unit. So in dark gray, we can see the QPU itself. And in light gray, blue, and white, we can see the embedding of our Kubo onto the QPU. On the right, we can see the click minor embedding, which tends to be a little bit more structured from what can be optically observed. And on the left, a little bit less structured heuristic minor embedding. And the click embedding is actually opting for making the chains of qubits shorter, because we want the chains to be shorter to make more optimal solutions. The pictures are with D-Wave Inspector tool visualization. So yes, so here I have a picture of logical qubits and a sample chain consisting of nine physical qubits. And I presented how it relates to what I have spoken. Now we would like to present some histograms to also gain some intuition. On the right, this is a histogram of a binary division of a graph of 100 nodes, just a binary one, not recursive. We've taken 100 samples. The numeric parameter, which indicates the number of samples that we take from the solution landscape, or actually how many times the quantum annealing process was done. So it was 100 in this case. And we can see the histograms. On the right, the histogram for the click minor embedding, and on the left, the heuristic one. And we can see that for click, the density of the histogram is shifted slightly more towards lower energy solutions, so indicating like better chances of getting a better solution. We have implemented access to the 2 approaches in Qommunity library, so the heuristic embedding and the so-called click embedding. And what we observed is, due to the fact that the click embedding is cached on our desktop, we reduced some execution time that can be seen on the right. And we also see stability of results and actually even improvement of results obtained with the advantage click embedding. Thank you for your attention. The project is now in a scientific article that is being peer-reviewed in the journal IEEE Transactions on Network Science and Engineering. And here we would like to present some QR codes that you can follow to check out the paper and the library.
Well, many thanks. Many thanks for this joint presentation. Well, now we have time for questions, for discussion, for suggestions. So I invite everybody who is with us to this part of the seminar. Well, before we'll find people who would like to ask questions, I would like to ask a question. Well, to which extent it is because the problem which was presented by Joan seems to be very general, in the sense that it's a topic which can have many practical implementation. Well, it make I think that also this library is not limited to this type of has a broader, even broader possible usage than just in this case. So it is something which goes beyond Cubo implementation optimization, or it's just limited to this? How it is universal, the library you have?
Sorry, I think this is related to Stefan's question, to the GraphCut approaches, no? Mm-hmm. Well, so the library only optimizes for modularity, right? The modularity function that I described. So that's what the library does. So if you input any other thing that is not the modularity function, or then I don't know what it will return in this sense. I think that probably we all think this, but I think I'm going to say more like a personal opinion on this, is that the real advancement here is that you can use advantage as many times as you want. So it's not a one-time process only. So you have to optimize the full problem at once. Mm-hmm. And we show that this works actually quite well. And this could be general, no? In fact, like in terms of classical algorithms in general, and also for community detections, they are all processes. They are never in and out in one step. So in this sense, this is the same. The generalization or that you mentioned probably can come from this fact that you can use advantage as many times as you want in a classical algorithmic way. I think that's the generalization that can happen. But you have to be sure that you're all the time optimizing the correct function. You know, this is something that we struggled at the beginning, but we realized that the recursive process can't optimize the same function always. You need to find relationships between the optimization, the cost function, let's say, in the current step of your hierarchy with respect to the previous one, so that you can be sure that the optimization, the full process is actually correct.
Well,
yes.
We have a question from Stefan, but maybe it would be it's a kind request to Mateusz. Maybe it would be possible to enable Stefan to ask the question directly. So
hi, do you hear me?
Hi, Stefan. Hello.
Hi all. Thank you for this presentation. Yeah, my first question was because you didn't mention graph cut optimization, whether there's a connection between your research and these graph cut approaches. That's one question, and the other one that I just typed into the Q&A is that I see possibilities to apply your approach to image segmentation as well, because if you build a graph from a regular grid of voxels and you inspect a connectivity between voxels that have a semantics making them connected, then you could even solve segmentation problems, right?
Yeah, thanks. I don't know if so maybe the second one is easier to answer. Yes, yes, I think so. As long as you encode the image as a graph in a way that makes sense, so that your communities have an actual are actually related to the segmentation that you want to do, we don't see any problems with that.
Okay, then you answered the first question, because then there is a relation to graph cut optimization, because there are graph cut segmentation algorithms published, which consider such a image as two graphs, one of the background graph, one of the foreground graph, and then you can investigate the graph. And I think the question would be now to not just use binary images, so foreground, background, but also many segments. And then you are very close to the problems that you address with your functional regions in the brain.
So I said that it wasn't that easy for me to answer, because it is definitely related with the graph cut, but I don't know if it's exactly the same or it's just
I can take this question.
Yeah.
Hello? Can you hear me?
Yes, Kasia, go on.
Okay, so this minimum cut problem, I think the community detection is similar, but in minimal cut you have a partitioning problem, so you search for minimal cut, but with the subgraphs or graphs that have similar size. So like in partitioning problem, you want to partition your problem into the pieces, so each piece is more or less the same. So for example, if you want to partition some data on the processors, yes, you want to each of the processor to have the same amount of work, and you want to make a minimal connection between the pieces between processors. But I think all these problems are quite similar, so you can think of applying this hierarchical approach to other versions, I would say. So I wouldn't say no, that our approach is not good for partitioning problem or any other version of minimal cut, but we simply haven't looked at it in detail, so we don't know exactly. But to be honest, there are many different versions of this cuts. So we specifically doing with this community detection thing, and we know more or less how it behaves. Yes. For the rest, we have to think of more.
Yeah, thank you. Nice research.
Thank you, Stefan. I'm very curious how about your experience with implementation all of this on D-Wave. How was it just direct, or it was some complex operation in this? Well, it's a question to Kaper and Barbara.
Well, from my perspective, it was simple because we were using Python to implement that, and the API to the D-Wave solvers is pretty clear because the documentation is rich. So we didn't have any problems with that, at least from my perspective. I don't know, how about you, Barbara?
Yes, the overall experience was pleasant. However, there are some limitations that come from the communication with the solver, so the cloud communication, and it's also related to the times that we elapsed of our method. That actually, we do not only have the quantum time on the quantum processor unit, but also the communication, the time of the programming on the quantum processor unit. and also the queue, because currently there are no such things as sessions that we get access to the QPU and can perform as many actions as we want, but it's rather on the system, queue-based system. So this is also some time limit that is related to it. But yeah, it was quite simple due to the Python API.
Okay, many thanks. And we have also Wiesław in. Wiesław, can you go on with your question?
Okay, thank you, Marian. Okay, thank you for your presentations. From the images, I understand that you can parcellate the brain, and I think it's obvious that there is this parcellation of the white matter, but can you also parcellate the gray matter, especially the cortex? And if yes, what would be the difference, the main difference between your parcellation and other existing parcellations of the cortex?
Thanks. It's a good question. So you can parcellate the gray matter as long as you express the problem as a graph. So maybe morphological graphs would be what is called morphological graphs, morphological networks could be used to parcellate the gray matter. I think that the main difference that if we did this, let's suppose we can do this, and we actually get a good parcellation in terms of that we have reached the optimal maximum, which is a good supposition, but let's suppose that's the case. The difference would be that the final parcellation would be the result of hierarchies. So we would have exploited the hierarchies in the original network to somehow take into consideration basically the hierarchical structure, no, the dependencies of at different levels. That there are there are a lot of them in neuroscience. No, the final parcellation would be better or worse than other available. I think it's not that easy to answer, but the main difference would definitely be that we would be exploiting hierarchies in the network, and hierarchies that actually are specifically and precisely defined with respect to the optimization, to the optimal modularity at every step of the process. I don't know if this can tell you more or in a more precise way than other existing parcellations. That would have to be researched. But my hypothesis is in the brain, in the neuroscience especially, the hierarchies are informative rather than just the endpoint. So in this case, it could provide slightly more information than just a start to end approach. I don't know if this is somehow answers your question.
Yeah, it's very interesting. Of course, we know that there are many hierarchies, many loops in the brain. So so of course, any approach which can localize them would be very, very helpful. Another question would be, many brain disorders are related to changes in white matter. Do you think in maybe some long run that your approaches might be useful for the early detection of neurologic disorders?
Yes, another great question. I think that this would be like ideal. Probably the stock market would skyrocket in terms of quantum technologies if that would be the case. However, even using classical computing, this is still an ongoing research, no? So we have we actually have another paper in review that uses modularity, among others, to try to detect Parkinson's disease from early sleep disorders, early sleep disturbances. So given that the modularity would be another indicator from and can be derived from white matter structure, Yes, why not? No. So again, if we suppose that all the hierarchy is informative of the disorder, why not? No, we have to be sure that the quantum devices can solve the problem good, accurately, in reasonable times. And then it's just a matter of, I would say, scaling and testing whether the method itself, rather than the quantum computing, can be useful. I don't know if you would agree with this, no? So
Yeah, I see that you have a wonderful and exciting niche of research. So of course, I can only wish you good luck, and hopefully more people will be working in this field to have actual clinical breakthroughs. So good luck. Thank you.
thank you.
Thank you very much, Wiesław. Well, I think that it is a good example of joint research efforts between Sano, Faculty of Computer Science, and Cyfronet. So I think that it's something what is worth to be followed somehow. So it's to do something which is of, let's say, high quality from the scientific point of view, and also of practical usage, because I think that the library can be used for many other purposes, and it's really something very good. We had, well, we do not have more questions, so I think that it's time to thank Barbara, Kacper, and Joan for talk. Very inspiring, and well, Wiesław and Stefan for participation in the discussion, and also many thanks to Kasia, who, as I understand, was supervising Kacper and Barbara. Yes.
Thank
This
you.
was actually a very interdisciplinary project. Yes.
Oh, well, I think that good science is interdisciplinary. It was a good example of this. Many thanks. Well, our next seminar will be in a week from now, and it will be a kind of presentation how Sano contributed with something like 7 or 8 posters to conference of users of Cyfronet. So many thanks, and see you in a week from now. Thank you very much.
Thank you for the invitation very much.
Thank you.
For the chance.
Thank you
Thanks.
very much.
Thank you. Bye-bye.